So we're going to start out our talk today. I mean, this is all going to be on nilpotent algebras today. For maybe a couple videos. I don't know how long this chapter is here, but nilpotent algebras. And so our default here, K is a commutative field. And all the algebras are finite dimensional over K. What is a nilpotent Lie algebra? A Lie algebra G is nilpotent if there exists a decreasing finite sequence of ideals so this is Gi from I equals 1 to P of G. Yes, that notation is a bit wrong here. G such that this additional G0 is just G. Our last ideal GP is just 0. And I guess I'll just change the indexing to be from 0. And the bracket of G and Gi is contained within Gi plus 1 for 0 less than or equal to I is less than P. And of course, all commutative Lie algebras are of course going to be nilpotent because the bracket is always going to be 0 and every ideal of G has to contain 0, so yeah. Proposition. The following are equivalent. Well, A, G is nilpotent, so this is essentially we're going to be listing alternative definitions for nilpotency of G. B. Okay. Oh, we didn't cover central series. Alright, I'll go back and cover that in a second here. For now, bear with me. So CK of G is 0 for sufficiently large. I will go back over this once we have our definition of C. C is C to the K, C, the lower central series of G equals G for sufficiently large K. There exists a K in an integer K such that the adjoint of x1 composed with a bunch of other adjoints all the way up to xk is 0 for all sequences x of k elements. So essentially, if you compose k adjoints, you get 0 no matter what they're the adjoints of. And E, there exists a decreasing sequence of ideals, which we're going to write gi from equals 0 to n. This is a g. This is very similar to our original definition of nilpotents. But we also have this condition that, as we'd expect, gi is in gi plus 1. But there's also the interesting conditions are that the dimension of these ratios of gi over gi plus 1 is equal to 1. Now, side note, we need to talk about the essential series. I need to find where they talk about that. So you'll have to hang on with me for 1 second, because this was something I think I ended up glossing over, or maybe I did cover it, but it was long enough ago that it deserves a review. Okay. Ideals. Do they never define? Okay, they do. Alright, here we go. Quick sidebar here on the lower and upper central series. The lower central series is the decreasing sequence of C1G, C2G, and so on, of characteristic ideals of G defined as, well, our starter C1G is just all of G. Second is that then inductively C plus 1 of G is the bracket of G and CP of G. We also have related is the derived series. A decreasing sequence of D0G d1g and so on of characteristic ideals of G defined as, first off, d0 of G is equal to G. Then secondly, dp plus 1 of G is again inductively, this time it is the bracket of dpg with itself. We see that C2 of G is equal to the bracket of G with C1 of G, which is the bracket of G with G, which is the bracket of D0G with D0G, that spells dog, which it gives us D1 of G. We also see inductively that each c to the cp plus 1 of G contains dp of G. And before we move on, let's do a little discussion of this here. Proposition G and H be Lie algebras over K, and this all applies for arbitrary K ring in this discussion because this is from an earlier section. And F from G to H a homomorphism. Then F of dp of G is equal to dp of H, and likewise F of Cp of G is equal to Cp of H. Proof is it's obvious from the fact that F of the bracket of two submodules is equal to the bracket of the images of those submodules, and this is just, you can see this by just calling it the bracket of subgroups is done, subsets is done component-wise, and that a Lie algebra homomorphism has to split across the bracket like this. There's a corollary that G be a Lie algebra with ideal A, then G over A is commutative if and only if A contains the DG. And just a reminder, I don't know if I wrote this, D1 of G is just DG. This is the bracket of G with itself. So if every bracket of G with itself is contained within the ideal you're modding out, it's commutative. The proof: G over A is commutative if if the derived series of g over alpha equals 0, which holds as dg over alpha is the image, canonical image of dg in g over alpha by, once again, that injection being done by a homomorphism which will behave well with the bracket. Now finally we're left with the upper central series, which is a bit of a messier definition, but still important. Let G be a Lie algebra, P and G just a subset, with no guaranteed structure. Recall the centralizer of P centralizer P of G. I guess that's backwards, isn't it? The centralizer in G of P is X in G, where X, Y where X permutes with all X permutes with all of P. This is the intersections so this, I guess, is better phrase it saying that the bracket of X with all of P is just 0 of the kernels of the adjoints of the elements of P and so is a subalgebra of G. We have ourselves a proposition. So we're going to let G be a Lie algebra with a potentially characteristic ideal A. Then A prime, which is the G centralizer of A. We may have covered this already, but it's worth reviewing in any case. Is a characteristic ideal of G. Proof, let D be a derivation. That's going to be an derivation. It's going to be an inner derivation in the case where the ideal is not characteristic. of G. If x is in A prime and y is in A, then the bracket of dx and y is equal to the d of x comma y, bracket of x and y, minus x bracket dy, which is going to be equal to 0. So d of x is an alpha. Alright. So, I don't know if we need to go through all that, but it's worth reviewing. I think the upper central series finally is the increasing sequence from C0 of G, C1 of G, and so on, of characteristic ideals of G defined as, well, in this case, C0 of G is actually just the element 0. And the second part is real messy. I gotta figure out a good way of writing it. So we're gonna let pi p be the mapping of G mod CPG onto the center of G mod CPG. So essentially modding out the, I believe that is dividing by the ideal generated by the bracket of that with itself. No, okay, no, that is not right, actually. This is a mapping, this is much easier. This is a mapping from G onto G over CP of G. Then CP plus 1G is the inverse image under this map of the center of G over CPG. This is a definition they give. We see that C1 of G is just the center of G. This is a definition they give. This works as a definition, but there's another way of thinking about it which is easier, which I have to pull up. Okay, give me 1 second. Upper central series of Lie groups. Equivalent definition, which I went through the proof before I had to work through it manually. I don't know if I'm going to list it again because I don't have it on hand, but I have checked that this is equivalent. We let C0 of G be equal to 0 as before. And then we have, I believe, I'm sorry for the delay, that I plus 1g is the set of x in G where the image of G under the of all G under the adjoint operator of x is contained within the previous G. I'll put a note here that you should verify this yourself. Not guaranteed to be true because this is something I'm recalling and not that I'm getting from an official source. But this is kind of, if you can get this, this is a better definition to work with, I find. Alright, so now let's go back to our discussion of the definition of nilpotency. So we have here 5 equivalent definitions here. You can have it as that saying that G is nilpotent, a very easy definition. So we're saying that either that both the upper and central series terminate in kind of the place you would expect, that you can that the composition of n adjoints for any n elements of x gives you 0, and that you can find a decreasing sequence of ideals where the bracket of G and Gi is Gi plus 1, and each Gi kind of going forward by one ideal essentially strips off exactly one dimension of our ideal. So let's look at the proof. If ck is 0, if the kth element of the lower central series is 0, which you can show that one terminates if and only if the other does, although they're not going to line up exactly. Then, like, the length of the series will line up, but the contents won't necessarily just be flipped. Then clearly C1 of G through to CK of G satisfies the definition of a that is, it is a series of decreasing finite ideals that the bracket of G and Gi is inside Gi plus 1. Especially CK of G is decreasing up to C0 of G. Hence, G is nilpotent. Conversely, so G is nilpotent here. So suppose G is nilpotent with the decreasing sequence of Gi from I equals 0 to P. Then inductively, we have that each of these gi must contain c to the I plus 1 of g, and that g to the p minus I contains the c to the I of g. Hence, c to the p plus 1 of g is equal to 0. And the pth term of the lower central series, the upper central series, is g. Thus, we have the nilpotent definition if and only if the lower central series terminates, if and only if the upper central series terminates. Now, let ci of g, now we want to show for d, which is that there's an integer k such that the composition of k adjoints is equal to 0. Let Cig be the set of linear combinations of x1 bracket through to x to the I minus 1 with xi. This is equivalent to the lower central series so we get b if and only if d. Just keep in mind, just note that c0 of g of this, c1 of g of this linear combination is just g, and that c to the I plus 1 g is just d bracket with any g, and then you can have I terms in the middle, which is an element of c to the I g. So that just reduces down to being the lower central series. Finally, condition E was that we have a descending sequence of ideals that meets the definition for the nilpotent, but also has the quotient of successive ideals have dimension 1. So we always reduce down dimension 1. And since it includes the definition of a series of ideals that makes it nilpotent, E implies A trivially. So you want to show that A implies E. So we have gi, I from 0 to p, with the properties desired. T's of A there exists a decreasing sequence hi from 0 to n of vector subspaces of G of dimension n minus 1 descending down to 0, and a sequence of indices of I0 less than I1 data to IP. With essentially what we're doing here, so G0 is HI0, so essentially GP is HIP for all P. Essentially what we're doing here is our GI has to contain G to the I plus 1, And so it's going to be some dimensions lower as you go on. And so you just break that quotient down dimension by dimension. Like this. Then as the bracket of G with HIK is in HIK plus 1. The HI are ideals. And G to the HI must be contained in H to the I plus 1 for all I. Thus, A is equivalent to E. And that is the end of our proof. Since we're starting a new topic that's so basic, it's I never know how far to go. There's 4 small results. We'll just do them. Why not? So, corollary. Non-zero nilpotent. Non-zero nilpotent Lie algebras always have non-zero centers. Corollary 2, nilpotent Lie algebras have a killing form, which, as we recall, is the trace of the product of the killing form is a bilinear form, which is the trace of the product of the matrix forms of the adjoints of its 2 inputs. And it has a killing form of is just 0 on a nilpotent algebra. For all x and y in our algebra G, the composition of add x and add y, which is the same as the product, is nilpotent. So essentially there exists a natural K such that add x composed with add y to the K equals 0. Hence has 0 trace, because I'll have to look. I'm pretty sure the trace of a product is the product of the traces. Maybe. At least. I should look that up before I say it too confidently, but yeah, the trace, no. But we do have the we don't have that directly, but we do have conditions that will give you that. Like, for example, the trace is the sum of the eigenvalues, I believe. Maybe. Don't trust what I just say off the cuff too closely. Proposition. Subalgebras, quotient algebras, and central extensions of nilpotent algebras. I'm going to abbreviate every word in this sentence. Are nilpotent, as are finite products of nilpotent. Finite products of nilpotent Lie algebras. Let G be a Lie algebra with subalgebra G prime ideal H T equals G over H, and phi the mapping of G onto T canonical. If G is nilpotent, then the kth lower central series element of G is 0 for some k. For some k, hence ck of G prime is 0, and ck of T is equal to phi of ck of G, which is going to be 0, which gives us that subalgebras and quotient algebras are nilpotent. If T is nilpotent and H is contained within the center of G, then ck of T is 0 for some k. Hence, ck of G is in H, so ck plus 1 of G is contained within the bracket of H and G. Since H is in the center, this is just 0. So G is nilpotent. In this case, I believe T is our base algebra, G is our central extension. That's nilpotent. And we get finite products by the adjoint composition definition of nilpotency, which we went over in our proposition. That was our first proposition. That is the end of our proof. And we see nilpotent Lie algebras are the algebras obtained by sequences of central extensions of commutative Lie algebras. And there's one last proposition, kind of an easy one. Let G be a nilpotent Lie algebra with subalgebra H such that H is not G. Then the normalizer in G of H is not H. And recall that the normalizer is just a set of elements in G such that the bracket of G with H is contained within H. And the proof let K be the greatest integer such that Ck of G plus H is not H. So this of course means Ck of G cannot be 0. And also that it cannot be within H. And the bracket of Ckg plus H with H is contained within Ck plus 1g plus H, which is in H. And so Ck of G plus H, which is not H, is inside of Ng of H. And we're done, and we will break it off there for today. Next time, Engel's theorem. Engel's theorem, maybe consequence or two of that. Look forward to that, I guess.